So our next presenter is Jerry Schnoor. He's the Alan S. Henry Chair in Engineering at the University of Iowa. Jerry received the Clark Prize in 2010 for improving human management decisions to reduce negative impacts on water. You know, he's had so many accomplishments in his career. He's always been engaged in developing new interdisciplinary programs. He's currently co-directs and he founded this Center for Global and Regional Environmental Research. He started out his career in looking at chemical contamination. He just chaired a very important, I think, report by the National Academy of Sciences talking about science for environmental protection in the future. And he's just, advanced science communication. As most of you know, he's the editor-in-chief of Environmental Science and Technology. And not only has he done an excellent job with that journal, but he's also used the editorial page to really talk about important issues in science and engineering. So Jerry, please come talk to us about climate change and energy. Thank you.
Thanks very much, Joan. It's a pleasure to be here, and my compliments to Jeff Moser and the NWRI that this conference is becoming really quite a special occasion, and it's really a joy to be here. Thank you very much. They asked me today to talk about energy and climate and perhaps effects on water resources and water supply, so I'll try to do that. It's maybe an easy backdrop this week with the tragic news of Typhoon Haiyan in Philippines, maybe the biggest storm of its kind ever recorded, and of course with tragic consequences. And regarding water resources, we might ask the question, well, is that caused by climate change? And as you know, of course, the answer is you can't attest to any one event as being caused by climate change, but you can say that in terms of hurricanes and typhoons, the high Category 4 and 5 type storms do seem to be fed by warm waters, and we do have warm waters now as a result of climate change. Some of the other effects on water resources that we're going to talk about today are maybe even more emphatic and statistically significant. The storms of the kind in the Typhoon Haiyan are a little bit more problematic, but indeed disastrous. So the drivers in changes in water sustainability maybe are 5. You could parse it different ways, but here's one way to do it. And today we're looking at 2 of the more important ones, I would say, of the 5 drivers in making our water and water supplies become perhaps more unsustainable. Climate change is the first one that we'll talk about, and as you know, it's causing rises in temperature, but the average increase in temperature is about 0.8 degrees Celsius so far. Not so much, and it's not really the average that we're too much concerned about with respect to water resources. It's more the extremes. In general, while it is warmer, there's been shifts in precipitation, and that's more important for our field, I would say, and increases in the extremes of that precipitation. And as was said by David Sedlak earlier, wet areas are getting wetter and dry areas are getting drier. I'm not a climatologist, and I didn't sleep in a Holiday Inn Express. I stayed in this beautiful hotel last night, but I work really closely with climatologists, several of them, and we're right now using about 12 different GCM models and about 6 different regional models embedded in those to try to look off into the future, maybe to 2050 or 2070. And that's what we'll talk about today. There's good reason why wet areas are getting wetter and dry areas are getting drier, and that is because wet areas are getting wetter because the whole planet is getting wetter. The Earth's surface is warmer, That causes more evaporation. More evaporation causes more moisture. Our dew points are going up. You can see it very clearly in the satellite data from the AIRS instrument, the infrared instrument on the Aqua satellite. And that's causing more intense precipitation. So rainfall rates are up. Global rainfall rates are up. Wet areas are getting wetter, but also dry areas are getting drier because, like in the coastal desert of California, if you have just a little bit of moisture in the soil and you hit a warm period, that moisture evaporates much faster than before. So that's the tendency towards increased drought and dry areas getting drier. Now, I suppose the backdrop to the whole story is global emissions. Unfortunately, in our lifetimes, they've just gone up, 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 and up. And the day when we are able to turn this curve upside down should be a day of global celebration, because it really is the charge in the 21st century, and the charge to our young people in the audience is to turn this curve around. Not only turn it around, but have an 80% decrease in the next few decades. So to go from currently about 50 billion metric tons per year of greenhouse gases emitted down to, say, 10 or so. And that's only in order to level off our greenhouse gas carbon dioxide concentration at 450. So that's just to stabilize it. We need an 80% decrease in emissions. It's a daunting challenge indeed, and one that will be a cause for great celebration. And there are some hopeful signs which we'll get to today. Usually when I give a talk on climate change, I only show the data because I find that people kind of turn off when you show them the models, but I will show you some models too, because we need that in order to project out to what could be effects on water supplies and water resources. But the upper right panel indicates how much warmer it's become in the last 100 years or so. California is about at the average, about 1 degree Celsius warmer over that period. But again, it's not the average, but the extremes that we're most concerned about. My climatologist friends that I do work with and that do sleep at Holiday Inns, they say that this is the smoking gun here. That when you talk about weather, you're talking about the day-to-day, what we see outside. When you talk about climate, you're talking about decade to decade, century to century, millennia to millennia, and yeah, hundreds of thousands of years between ice ages. And we think we understand a lot about those natural changes, but this is really wholly unexplained otherwise, the rate of temperature increase. And we've got 3 data points. The 80s were warmer before, the 90s were monotonically increased, the 2000s. Now there's a bit of a pause right now, and we think we understand that pause as well. It looks like a lot of the heat that's being generated, there's more. If I could do an ideal experiment, I'd poise a satellite at the edge of the atmosphere, and I'd measure all the energy coming in, and I'd measure all the energy going out, but I can't do that experiment. So the next best thing is what's being done in the Argo program, and that is to do essentially the same thing at the ocean surface, measuring all the radiation coming in and all the radiation going out, but doing it very, very precisely. So since 2005, I think this is maybe lost on the public, since 2005 we have really good data on this. We know with certainty that there's more energy going in than going out. It's about 0.7 watts per square meter. That may not sound like much. That's about a quarter of a standard Christmas tree bulb, 0.7 watts per square meter, shining on every square meter of the Earth continuously. I'd like to do the experiment that is in the literature that if we could all hold 40 hair dryers, all 7 billion of us, point them down into the ocean, switch them on 24 hours a day, 365 days a year, that's how much heat we're adding to the ocean. It's a lot of heat. Now, we couldn't do that experiment, of course. Not only could you find 40 hair dryers, but that's 20 times the amount of energy, the primary energy consumption of the planet each day. 20 times the amount of energy is going into, that we use each year, is going into the ocean. So it's really It's really incredible. And it's resulted in about a 1 degree Fahrenheit sea surface temperature increase shown here just in the last 50 years. And we can see that signal in the Atlantic. You can see it really clearly down 700 meters. It's a top-down warming. It could only be caused by humans. It can't be caused by ocean circulation or anything else that we can think of. And that warming, if you, even from the Argo buoys, if you measure the top 2,000 meters of ocean, that's most of the ocean, it amounts to a 0.06 degrees Celsius increase in the entire ocean in a 50-year period. So we're really out of balance. We're really, even though we're just at the beginning of this thing called climate change, we've got 3 data points, the 80s, the 90s, the 2000s. We're just at the beginning of it. It's still resulting in very large changes. That's not to mention the change in the pH of the surface ocean, which has gone from about 8.2 when I was born to about 8.08 today, which is roughly a 30% increase in acidity. If you were to have told me when I graduated from Iowa State University in 1972 that we could change the pH, the chemistry of the entire ocean in my lifetime, I would have said, no way. That's not possible. That's just such a huge thermal mass. It's not possible. But we're doing it. Again, the climatologists, they don't worry too much about the means. They haven't changed too much yet because we're just at the beginning of this. They worry about the extremes, and the extremes are changing. This is a plot from James Hansen paper in 2012 in JGR. The orange, I don't have a good pointer, so forgive me, but the orange is on the right-hand plot is 0.5 standard deviations warmer than a 30-year average in the record from 1950 to 1980, taken as the baseline for the anomaly. The red is 2 standard deviations, and the dark red is 3 standard deviations. So you can see the increase in recent years, up to about 10% of the Earth in any year is 3 standard deviations hotter than the normal. Wow. And what's more, the orange, about 80% of the Earth is 0.5 standard deviations warmer than 1950 to 1980. On the other hand, do we still have some cold weather? Sure, we're always going to have cold weather, but it's going to be much, much less frequent. That's shown by the purple, the blue, and the light blue on the left hand. The 0.5 standard deviation shows a slight cooling, only occurs now in about 5 or 10% of the places on Earth in any given year. So the area of stations that are experiencing cold weather is very small, slightly cold, and the area that's experiencing very hot weather is larger. Another kind, and maybe more important to us, is not the temperatures but the precipitation. And this is a map, again, in the last 50 years, say many of our lifetimes, of the increase in the 1 percentile events. And you can see that especially the Midwest and the northeastern United States are experiencing these intense precipitation events. Climatologically, we think we understand that. There's much more high cloud formation now, which is responsible for these intense events. In Iowa, if I look back at the record, it goes back about 130 years, and I look for a 4-inch daily event that's 100 millimeters, I'm hard-pressed to find one. Now it's quite common to find 4-inch event in a day, and that's the story that we're seeing. It hit us about 5 years ago. This is Cedar Rapids near the University of Iowa, completely flooded the downtown, billions of dollars of damage, and we're still not back yet. If you look at the record, you know, the record goes back, say to 1896, and when I was a kid, we used to say that we got 32 inches of rain. I can't make this pointer work, which is somewhere in the middle of the record. But in fact, it's gone from about 28 inches of rain in 1896 to about 36 or 37 inches of rain in recent years. But it's not, again, the trend. The average slope isn't the issue. The issue is, what are the years where we might have flooding, or what are the years when you have damage to a corn crop, say? Well, the first 50 years of that record, we had one event more than 40 inches, 1 year more than 40 inches. Now, in the last 50 years of the record, we've had 10 events more than 40. So again, it's the extremes. That's what we're trying to adjust to. That's what's causing the damages. 10 times more extreme years than just early in the period. And these rain events have come mostly early in the year, in spring or early summer, before crops are canopied, so we're losing an awful lot of soil, an unsustainable amount of soil. Now, you know that thermoelectric power plants are the largest withdrawer. That's the blue in the top pie diagram, and irrigation is the second largest demand. I'm happy to say that total water withdrawals in the country are steady or even declining. California has a wonderful record for greater water efficiency and is leading the country in that regard. I think there's only one state that continues to irrigate more and more. I believe it's Nebraska, the last time I checked, and it's to irrigate corn ethanol, corn for production of ethanol. So there are some good things happening, but thermoelectric power plants and irrigation are the two biggest withdrawals. And of course, irrigation, the blue on the bottom pie diagram, is the largest consumptive use due to evaporation losses. The irrigation withdrawals are shown county by county on the top map, and of course they're mostly in the western half of the United States, and then in Arkansas in the Mississippi River alluvium for irrigated corn, again, primarily. And in the bottom, that's the thermoelectric withdrawals, and they're, of course, distributed more widely across the country, especially at large coal-fired power plants in the eastern half of the country. Now, when we look at the models, this is a bigger suite of models than I'm using. This is a total of 16 general circulation models, or GCM models, in a paper in ES&T last year by Roy and Chen et al. At Tetra Tech. And it's quite a good paper if you can take a look at it. It indicates that all the models agree that the Northwest and through the northern part half of the country, and especially down to the southeast, is going to be wetter. The models agree on that. But they don't agree on California and the southern part. Only a couple of the models say that it'll be wetter there. And those that say it'll be wetter, it's a part of this increase in global rainfall rates that I mentioned earlier. Probably it'll be drier. The water withdrawals projected out in the same paper are shown here. And you can see to 2050, the dark areas are more than 10 inches of precipitation withdrawn from all sources. And it is a national problem, again, given the thermoelectric power plant withdrawals as well as irrigative withdrawals in the Central Valley of California. But if you look at water stress, which is maybe the withdrawals divided by the available precipitation, the dark areas here are 5 times more withdrawal than the available precipitation in the area. And you can see that it's especially the high plains area in the central United States and, of course, the western part, which has water stress in 2050, according to this report. They made a risk index out of it, a water sustainability risk index for water supplies, and the bottom map here shows if there were no climate change, if it was static from here to 2050, the areas that would be withdrawing more water than precipitation that falls, so they're in water stress. But if you superimpose on that the climate change effect, the title of this talk, then you get the top map, and a much greater portion of the country comes into risk of water supply by 2050. So climate change is changing already. I think you know that, but it'll more greatly affect water supplies by 2050. The climate models that I'm working with indicate that western and southern U.S. will be hotter and drier. There will be greater water stress here, for example, and a greater need for aquifer recharge and water reuse, the kind of thing in our great keynote talk today by David Sedlak. The Midwest will become warmer and drier on average, but it'll be punctuated by these severe precipitation events for the reason that I talked about. So you get the worst of both worlds, and you have to adapt to that. And the eastern United States will be warmer and wetter, and of course flooding events are the issue. I'm 6 days ahead of you, Dave Sedlak. I'm showing the Drought Monitor from November 5th, and of course today 1/3 or almost 1/2 of the country remains in drought, so we have to figure out how to plan for that with our water resources and our water supplies. Energy production is also changing, as you know. Coal-fired power plants are on their way out. We closed 20, we had 440 some coal-fired power plants 5 years ago, and it's in the mid-300s now. We've closed 20 gigawatts of capacity in just the past 5 years. What's replacing them is mostly gas-fired power plants, and to some extent wind and solar. And wind and solar in particular are more water efficient, and the gas-fired power plants can be somewhat more water efficient also. But our domestic energy production is up, as you know. That's in some ways a good story, but it means that we have to have more water for both conventional and non-conventional oil and gas exploration, as well as for biofuels if we're going to continue that program. This shows the transition in the electrical sector, with coal being down, natural gas being up to almost rise to replace the loss from coal, and non-hydro renewables, mostly wind and solar, also being a part of that makeup. Don't ever let anyone tell you that we're going to run out of oil or conventional gas. We've only used the purple 3 bars of conventional oil, gas, and coal on this plot, and the y-axis is in billion of metric tons of carbon of those resources, and we've got the blue, the known reserves, and the yellow, the probable reserves, still in store. We dare not go there, because if we do begin to burn the blue and the yellow, we reach carbon dioxide concentrations in the atmosphere increases on the y-axis on the right-hand side that would throw us into a climate never seen before, perhaps since the Pleistocene 50 million years ago. We dare not go there. We must transition from the fossil fuel age, and that is the challenge for us in the 21st century. And I tell my students it doesn't need to be onerous. It doesn't need to be painful. It doesn't need to be, make people poor. Rather, it can be the economic engine that drives our economy, this great transition that's going to take place in the 21st century. Refining crude oil bitumen would not be a part of that revolution in my eyes. I wrote an editorial recently called Keystone XL Pipeline to Nowhere. Not because it doesn't go anywhere, it does. It goes to the Gulf Coast, where it will be exported as refined products. We're a net exporting oil country now in the United States. But rather, it's a pipeline to nowhere because economically and strategically, it's not the way to go. It's not the future that we need. We don't need that oil. What's more, the energy efficiency regulations on automobiles that the Obama administration and the auto companies put in place will save more than 2 times the oil in that pipeline by the year 2025. We don't need that oil. The key is energy efficiency, not the Keystone Pipeline. Shale gases may be a transition or bridge fuel, but it will require a lot of water. It's the greatest energy story, bar none, of the 21st century, but it requires regulation. You've probably seen this map. The pink color is all the active plays. We have one near our conference up in Monterey, and they don't, Rhodes Trussell and I talk about this, they don't have much water in Monterey either, and it's an interesting development. It's more oil than gas there in the Monterey Shale. Just to give you an idea what an operation looks like, this is 3 different wells. I don't know if you can see them. And I can't find a pointer, I apologize. Here, here, and here, that's 3 different wells. This one is going out 4 kilometers this way, 3 kilometers this way, and 3 kilometers this way. You can explore almost the entire shale unit for kilometers around due to the horizontal drilling which has been developed. But it needs maybe 3 to 5 million gallons of water. If you do this in the Pennsylvania Marcellus Formation, you get back something less than that. If you do this in the Barnett in Texas, you get back more produced and flow back water. And of course, you need to re-inject it, and there's issues there seismically. I don't know if you should really believe this or not, but it's from Chesapeake Energy, one of the oil and gas companies, but they list the good and the bad water users for energy development, top to bottom. So it's like golf. A low score is better because it's in the gallons per million BTU of energy produced. Shale gas is one of the lower water users, according to this plot, going down through conventional oil shale, the oil sands like in Alberta, Canada, and the worst is good old Midwestern irrigated biofuels. I had good fortune to chair a committee that I learned an awful lot from on the water implications of biofuels in the United States. And this shows that we've reached the planned amount basically of 15 billion gallons per year of biofuels, largely with corn ethanol. That's how we've done it, and that's the worst feedstock in terms of being a food crop, also in terms of the highest inputs of anything that you could make biofuels with. So it's not a happy story, really. It's like a good cop, bad cop. The cellulosic biofuels, which have promise of being more efficient in terms of energy inputs and fertilizer inputs and pesticides, they haven't shown up commercially. We don't have a drop of them yet at commercial scale. But the corn ethanol, the bad guy, we got the bad cop. We haven't seen the good cop develop yet. So it's not clear what's going to happen to the goal for 21 more billion gallons per year from advanced biofuels and cellulosic. Because we have done it with corn ethanol, that means more acres have been planted to corn. Not more acres total of agricultural land in the country, but rather other crops being converted to corn. And that means the high inputs cause runoff of nitrogen and phosphorus down the Mississippi to the Gulf of Mexico, exacerbating Gulf hypoxia. This is a typical plant, the Lincoln Way Energy Plant, not too far from my home in Nevada, Iowa. It's a modest size, 50 million gallons per year, but it uses 18 million bushels of corn. That's almost a county of corn around it, more than 100,000 acres around it. It uses 150 million gallons of water, and that's about 3 gallons of water per gallon of ethanol. And this is non-irrigated. This is rain-fed corn. So if this was in Nebraska and it was irrigated, it would be about 1,000 gallons of water per gallon. So when you put flex fuel in your car, 10 gallons, that would be really 10,000 gallons of water equivalent at the same time as you put the ethanol in. Dave Sedlak this morning in his keynote talked about the revolution maybe starts at a certain time, but then takes time to develop. And maybe in Kansas, as we withdraw water from the Ogallala Aquifer, maybe this is Wichita County right here, where the saturated thickness of the Ogallala Aquifer has gone to 0. There's no water that is obtainable in Wichita, Kansas right now. That's because they've completely depleted the aquifer at that place. And there's other places too in Kansas and Texas and Oklahoma with depletion time frames only a few years left. It's not only the high plains of the Ogallala Aquifer of the Midwest, but also the cities. Here, Chicago has withdrawn so much water in the last 100 years that we have an 800-foot decline in the Cambrian-Ordovician aquifer. And Minneapolis, or Milwaukee, about a 300 or 400-foot decline in the Cambrian-Ordovician. I'll skip this one. So all of this draws into question the renewable fuel standard and how we're going to finish this out. Somehow Congress has to save face, I think, and the whole program needs to be rethought, unless cellulosic biofuels can come on. So we have to make more judicious use of our energy choices, consider the water footprint as well as the greenhouse gas. We have to adapt to climate change and mitigate our greenhouse gases. I think we do that with the people who are willing to go now. I call it the coalitions of the willing. The citizens, the communities, the cities, the urban environments that are really relatively willing to act now. There is good news, 6.9% decrease in emissions in the U.S. Maybe in the U.S. we're beginning to turn that curve upside down for the very first time. And it's due to the efficient vehicles, 3 to 4% increase in efficiency each year, and due to young people who shop in a different way, who commute in a different way, and who want local foods. It's beginning to make a difference. I think the answer is hyper efficiency. We don't need 40 mile per gallon cars. We need 400 mile per gallon cars, which will fill up at night on solar power or wind, fill up during the day on solar power or wind power at night. We'll have more big wind and small solar on every building that's constructed. Natural gas might be a bridging fuel. If you can't accept that as a transition, then we'll have to have more nuclear, one or the other, to replace the base fuel, baseline electricity demand. And last, we need good government to provide an incentive for this transition that we're going to undertake, in which fossil fuels become expensive and renewables and energy efficiency by virtue of scale becomes much, much cheaper. In net, we'll be better off, and that will create the jobs for the future. I'm reminded in closing of the Chinese characters for crisis. There's danger here, I think, with respect to energy and climate, but there's certainly great opportunity, and I hope that we concentrate on the latter. Thanks very much.
Thank you, Jerald. I didn't have to pull you off the stage. That was great. Okay, the paper is open for some questions. Yes, Rhodes, you have a question over there.
So I just want to get some perspective on the extreme issue, because that's the one that's been concerning me the most. And you showed that plot on the increase of extreme temperatures.
That was global.
I recall you showed a 10% increase in events that are 3 standard deviations beyond the normal.
10% of the stations, so you could interpret that 10% of the area of the world has a year, each and every year, that's hotter than 3 standard deviations from the norm of 1950 to 1980.
So I want to speculate, what does that mean for events like, we experience, where
it means that droughts, like I say, the soil moisture is going to go.
I'm sorry, I'm a little slow formulating the question, but I want to get a little further on it. So, like here in the summer, when I was a kid, we had events where the temperature would reach over 100 degrees for 3 or 4 days every other year. Now, I think this year, I think in Pasadena it was 110 at one point. And I'm wondering, what do these extreme events have in terms of a meaning about survivability and what we'll have to do to deal with it, and how extreme are those changes going to be? And the models tend to talk about these long term, like you're talking about the year. Well, what about a week? What about a month? That's 130 degrees or something like that. Is that going to be possible in the course of the next 3 or 4 decades?
The models that we're using that go out to 2050 or 2070 from NCARD, do not show many events of that nature.
Well, I'm glad to hear that. Because I'm thinking this 3 orders of magnitude, 3 standard deviations. That's
hot.
Yeah. Well, I mean, that's. I figure that means an event that occurred once every 10 years now, or every 300 years now, occurs once every 10 years, if I got that right.
We're setting high temperature records 3 times more frequently than low temperature records today. But by 2050, we'll be setting high temperature records 20 times for every low temperature record, if that helps to put it in perspective.
Any other quick questions? It's a little scary, the changes globally.
But there's opportunity.
Yeah.
Okay, thanks.
We'll move on then. Thanks.